before that, we have Eunice from Victoria, who will tell us everything about Kerr black holes in the Sitter. Please.
Hi, good evening. Thank you for the opportunity in ICTP. I'm going to talk about black hole shadows. It's been a great day talking about gravitational waves and the observations of black holes by gravitational waves. Now let's move to the regime of Event Horizon Telescope. In this work, I shall present my work on remarks on Kerr black hole shadows in Kerr-de Sitter spacetimes. This work I have done with Professor Humberto, Giulio, and Emmanuel. They are based in PPG Cosmo. So I will give a brief introduction. I talk somehow about the Kerr-de Sitter spacetime, the Kerr-de Sitter revisited spacetime, and the celestial coordinates. I will also talk about the quantitative and the qualitative analysis of the black hole shadows that I shall discuss, and then give a conclusion. Black holes are regions where gravity is very strong. It is strong enough such that it can warp the spacetime and it can lead to the bending of light. So it is most probable that the black holes are rotating in nature and they are described by the Kerr solution. But then when we incorporate the effect of the cosmological constant, then we have the Kerr-de Sitter solution. The Kerr-de Sitter solution, it's a lambda solution. It has constant curvature, and then it belongs to the Klebanski-Demiansky class of solutions. And then recently, a new solution was proposed, not really discovered, proposed, and it is the Kerr-de Sitter revisited metric. So this metric, it has the cosmological constant, but the difference is that this metric is not a vacuum solution. It does not have constant curvature, and it doesn't belong to the Klebanski-Demiansky class of solutions. And then because of this, the authors named it the Kerr-de Sitter revisited solution. And so this spacetime, due to the cosmological constant, because you can imagine the Kerr black hole has just two horizons, the event horizon and the Cauchy horizon. Due to the presence of the cosmological constant, now these spacetimes have four horizons. And these are the cosmological horizon, the event horizon, the Cauchy horizon, and the dual of the cosmological horizon. For astrophysically relevant solution phenomena, another radius comes up, which is called the static radius, and this radius is going to be somehow important to our work. It's kind of the interest of this work. And so, what's a black hole shadow? When we have a black hole and there's a luminous background, the light that is coming from the luminous background can be projected into the sky of an observer, and it will cause a bright ring with a dark region in the middle, which I will not explain so much, and that's the black hole shadow. And then for an observer to locate the shadow in the sky, we need to define a set of coordinates with which this observer will be able to locate the shadow in the sky, and these are the so-called celestial coordinates. So the celestial coordinates, they depend sometimes on the nature of the spacetime. For instance, the Kerr spacetime is asymptotically flat, and therefore far observers can be considered. And in Kerr-de Sitter spacetime, this spacetime is asymptotically flat. So a lot of care has to be taken on the observers, and observers that are always considered in the literature in this spacetime are finite distance observers, because there's nowhere we consider it to be asymptotically flat. So just use the null tetrads and obtain the celestial coordinates. And then, what do we intend to do in this work? The tetrad formalism has been used. So in this work, we were trying to study something new, where we place the observers in this Kerr-de Sitter spacetime, we place our observer in the vicinity of the static radius. And then why do we consider this? So the static radius has a certain property which, according to me, I feel hasn't been so much studied, because in this static radius, we have that the gravitational attraction and the cosmic repulsion, they counterbalance each other on this radius. And then by the use of embedding diagrams, some authors have shown that the spacetime in the vicinity of the static radius in these spacetimes is analogous to asymptotically flat spacetime. So what I was doing with my supervisors is that we were trying to place observers in the vicinity of the static radius and treat this region as analogous to asymptotically flat, and we obtain celestial coordinates and see if this can lead to some astrophysically relevant black hole shadows. So that's a brief introduction and a brief review of the Kerr-de Sitter spacetime. This is the Kerr-de Sitter metric, and these are the proper, in Boyle-Lindquist coordinates, TR and TR, theta, and phi. And this metric doesn't depend on t and phi, so it has two Killing vectors, which we shall see shall be related to constants of motion according to Noether's theorem. And then, because this, we have equation 3, delta r, it's a quartic polynomial. This will lead to the 4 horizons of this spacetime. And then, because we've spoken that when a black hole is, when there's a luminous background, the light that is coming from the luminous background will be projected in the sky. So the relevant geodesics we will use are the null geodesics, not the time-like geodesics, because the light is massless, the photons are massless. So considering the null geodesics, in Kerr-de Sitter spacetime, they have been analyzed, and I've given them here. Specifically, the critical curve which we study in this work, it is as a result of null geodesics at a constant radius, and these geodesics have various names in the literature, and here we shall just refer them to the spherical photon orbits. So the condition for spherical photon orbits is that the radial potential, which is equation 10, it has to be 0, and its first derivative with respect to r has to be 0. Solving this equation simultaneously, we obtain equation 13 and 14. 13 and 14 are the constants of motions related to those two Killing vectors that we talked about, which I hope we remember. So these are the constants of motion that govern the motion of spherical photon orbits in this spacetime. Equation 10, this eta, is important to this work. We find that these two constants of motion, they control the motion of orbits in various ways, especially when eta is 0 or greater than 0, the photons are going to behave in different ways. For instance, when eta is greater than 0, here I've put an example of an orbit, some geodesics which I obtained in my other research. This geodesic is moving about. If you consider the black hole shadow, the black hole as a sphere, this geodesic is moving up and below the equatorial plane. So this happens when eta is greater than 0. But when eta is equal to 0, they will be confined on the equatorial plane. And so we can solve for this equation of eta equals 0 to obtain two radius, equation 15 and 16. This is the radius at which the orbits will be confined on the equatorial plane, and these are called the equatorial circular orbits. They can be moving together with the black hole in the same direction. They are prograde, and when they move in the different direction, they are retrograde. So equation 15 and 16, they form the lower and upper bound of the spherical photon orbits. So the spherical photon orbits can only exist from the radius at equation 15 up to the radius at equation 16. In between, beyond this region, they are not spherical. Okay, so that's a quick review of Kerr spacetime. It is the same review in Kerr-de Sitter revisited spacetime. We have the metric. It has 2 Killing vectors and 4 horizons. Those are the null geodesics. And then by using the condition of spherical photon orbits, we obtain the constants of motion that govern the motion of these orbits. And then remember, equation 27 still is eta. This parameter, it's related to the constant of motion. It governs, it's related to the energy of the photons. So when it's 0, they are confined on the equatorial plane. So we solve for that equation, for that parameter when it's 0. We solve for r to obtain the lower and upper bound of the spherical photon orbits in Kerr-de Sitter revisited spacetime. And so that is a very quick review of the spacetime. Let's move to the celestial coordinates. So by considering observers in the vicinity of the static radius, remember we are treating these observers in this place to be kind of in an asymptotically flat region. So we obtain the celestial coordinates for Kerr-de Sitter and Kerr-de Sitter revisited as these equations. And then something you can ask is, okay, you just did that. How do you know that then these observers are going to observe shadows that have the right behavior, if I can say so? Okay, so remember, here we are considering the spherical photon orbits to make the critical curve, which we are going to study. So if these spherical photon orbits get projected in the sky to make this curve has to exhibit the property of the spherical photon orbits that lead to it. So we've seen about these orbits having a lower bound and upper bound. And so when they get projected in the sky, each and every of these orbits goes to a specific place. So this curve, you can think of it as a collection of various radius of the spherical photon region. Especially at point D is where the lower bound, the smallest radius, which is defined by, for instance, equation 29. This radius, when it gets casted into the sky, it lies at point D of this curve, and the maximum radius lies at point R. The other radius in between will lie in between the curve, but I will concentrate on point D and R. So let's analyze the behavior of this, for instance, the radius in equation 29 and 30, the behavior that it will exhibit should be seen on these curves. So in this figure 3 and figure 4, I was analyzing the lower bound of Kerr-de Sitter and Kerr-de Sitter revisited spacetime. So when this spacetime, remember there's the cosmological constant. So we analyze the behavior for changing, A is the black hole spin. We are dealing with rotating black holes. And lambda is the cosmological constant. So as we see that as A is increasing, the radius is also decreasing. So we expect that at point D, this is where the lower bound lies. When we increase the value of A, the point D should be decreasing. It should be moving towards the left. It should be moving towards the left. Yeah, and so let's see. So for here, we analyze for the Kerr-de Sitter and Kerr-de Sitter revisited spacetime. We see on these curves, as we are increasing the values of A, this point, it keeps moving in the direction with which we see the behavior of its corresponding orbits. And then for changing lambda, we see that this lower bound, as we increase lambda, this radius seems to be increasing. So we expect that at point D, as we increase lambda, this point at point D, the orbits, the curve should be moving towards, it should be increasing, it should be moving towards the right. Oh my God. What happened? Okay, yeah. As we increase the value of the cosmological constant, the point D should be increasing. In that way, it should be moving towards the right. And then that's here we found like that's the behavior. So we analyzed the behavior of this of the radius of the photon orbits, and we found that using the celestial coordinates that we obtain, the corresponding shadows were showing this behavior. So that was kind of our proof that okay, whatever you just derived it's not invalid. It leads to relevant results. And then in the paper, we have compared some results with certain authors who had considered the same idea, not exactly the same, but they were considering the same idea. And then we found that the results they obtained were not revealing the behavior of the corresponding photon region. So the result was not correct, but then it doesn't affect the results of the article because that wasn't their main work. And then, so let me go to the qualitative analysis. Besides that, we also, because when you consider parametric curve, you can find the radius of curvature. So we derived the radius of curvature for this, for this critical curve at points T, and at point R, and we derived the vertical and horizontal diameters. We modeled this result to M87 results, and we find that for this astrophysically relevant value of the cosmological constant, the values are indistinguishable. They are only distinguishable when we use a larger value of the cosmological constant, but this is not astrophysically relevant. And then on the qualitative analysis of these shadows is that we used the Event Horizon Telescope. They released results of, on the constraint of the characteristic radius of the shadows. And then so they say that according to their results, the radius of the shadow shouldn't be less than 4.31, and it shouldn't be greater than 6.08. So we used these results to constrain the angle of inclination and the spin of the black hole. The angle of inclination is for the observer. And then when you see in these two figures, you see that for small values of black hole spin and small values of theta, the regions are the regions that are not permitted exist for high black hole spin and high angle of inclination. So we found that using this result, this constraint on the radius, we constrained the spin of the black hole, and we found that the spin, when it's greater than 0.812311, that's not allowed with respect to M87, and the angle of inclination when it's greater than 30.5107 degrees. These angles of inclination do not pass the constraints of M87, and therefore we found that the angles of inclination that pass are small, and also for small values of the black hole spin. Yeah, so that's what we did. We analyzed the black hole shadows. in Kerr-de Sitter and Kerr-de Sitter revisited spacetime, we considered observers in the vicinity of the static radius. By treating this vicinity as asymptotically flat, we found the celestial coordinates. We showed from our results that the celestial coordinates, despite our treatment, they satisfy the behavior of the corresponding photon region. We also analyzed quantitatively the shadows, and qualitatively we constrained the black hole spin and the angle of inclination. We find like the high angles of inclination and high values of black hole spin do not pass the test. So sometimes this disqualifies extremal Keck black holes from being observed by Event Horizon Telescope. Thank you for your attention.
Questions for Eunice?
Can you hear me?
Yeah.
About the figure 5 and 6.
Okay. Okay.
A is equals to 0.993.
Yeah.
Is there a problem around 1? Can you reach this point?
The problem around 1 is that when I need to use 1, the extremal Keck black holes, they need a different treatment, which we were not treating in this. So in this work, we were dealing with slowly rotating Kerr-de Sitter and Kerr-de Sitter revisited. We were not moving to the regime of extremal, because at 1, it starts being an extremal.
Okay. Okay. I think it's it's more about the problem is the computational or no?
It's not computational. No, for instance, the celestial coordinates which we obtained, when A is 1, I need to express them in a different way, which in the code I didn't. Maybe I was lazy.
Okay.
Yeah.
Okay.
So
Thank
it
you.
was just me not expressing the coordinates.
Thank you.
Yeah.
While we wait for the last question, please, all the poster sparkler presenter, please come down. So, but we have time for 1 or 2 more questions.
Thank you, Eunice.
Out.
I don't know if it's a silly question, but suppose that you have the greatest event horizon telescope and you could measure the shadow perfectly. Could you use, for instance, this metric to constrain the value of the cosmological constant?
Yeah, I've been trying to do this in my research, and I think it's kind of impossible at the moment.
Impossible.
At the moment.
But is it because of observation, or is it because you can't actually distinguish this metric from the Kerr one? I don't know.
Well, I really think it's because it's just small.
Mm-hmm.
Yeah.
Okay, thank you.
But with a better observation in principle, in principle you could measure with a better observation.
With the
Better observation.
maybe if they, they say that maybe if they move the telescopes to the moon.
That's better.
Okay, thank you.
Okay, so we thank you, Eunice, and all the speakers of the session.